Okay, hello physics students. This is Dr. Schultz, and I'm going to present a video lesson today called Using Velocity Vectors to Represent Projectile Motion. This particular lesson is going to be focusing on skills that you need when you're using vectors. And we're going to come back to some of the math skills that you learned in the last couple of years of your math classes, in particular using sine and cosine. We're going to be using sine and cosine functions to resolve velocity vectors into horizontal and vertical components. Also, we're going to be using the Pythagorean theorem. So given the x and y components of a vector, you're going to determine the vector's overall magnitude and direction. And then finally, we're going to talk some physics and see how this applies to projectile motion, which is the physics that we're studying right now. So let's start off with the idea that the velocity of any moving object can be represented by a vector. So we have here a picture of a ball or some type of an object which is moving with a velocity of 10 meters per second. If this is on a map, you could say that the ball was moving northeast. And you know that because that arrow represents the direction of the velocity of the object. The length of that arrow, of course, represents the actual magnitude of the velocity. And by now, I hope that you know that magnitude really is another word for size. So the magnitude of that vector is 10 meters per second. Now, we're going to find it very useful to take that vector and break it down into components. So this vector can be described in terms of its components in the horizontal and vertical directions. So the word component is a new word, and a component is a piece of a vector which lines up with the x direction, or it lines up with the y direction. So the vector that we have shown here actually has two components, an x component and a y component. Oftentimes the notation that we use is to call the x component vx and the y component vy. So we use subscripts. And so this should kind of make sense if you think about that object. It's moving. We said it was moving northeast, and that means it's moving both north and east at the same time. And so the components would actually tell us that, because we would be able to represent that motion separately. So this is really the first goal that we have in our lesson, is to figure out how do we actually represent those vectors, how do we figure out their sizes. So the process of finding the x and y components of a vector is called resolving the vector into its components. The word resolving means breaking down. And so we have a vector, again, which is a diagonal, and we want to resolve it into its horizontal and its vertical pieces. So we want to resolve it into its x and its y components. That's the goal. In order to draw a vector's components, you can simply box it in using a rectangle, and then you can draw the components outward from the common corner. So I think that this is really not mathematical at all, but it gives you a way of drawing components, which is usually the first thing you have to do in a physics problem. So if you have a vector that you've drawn, which is typically diagonal, what you would do is you basically just draw a rectangle around that vector, and the rectangle should be lining up with the x and the y axes. And then what you have is the x component of the vector is going to be the bottom part of the box. And so you would draw this red arrow, and you would stop the arrow at the end of the box. The y component you would sketch upwards until the top corner, and you end it right there. And so this is kind of a standard way of sketching components of a vector. Again, you begin by drawing the vector, you draw a box around it, and then the components are going to be two sides of the box. Do not make the components longer than the box edges. Do not make them shorter. You make them exactly equal to those two lengths of the rectangle. Now, if the magnitude of the original vector and its direction are known, you can use trigonometry to determine the magnitudes of these components. So here's where we get mathematical. So let's say that we know that the vector is 10 meters per second. That's its magnitude. Let's also say that we know that it's at 37 degrees above the horizontal. That's a very standard angle to give in projectile motion problems. Now what we want to do is find out what are the magnitudes of the x and the y components. So in other words, if you have a right triangle and the hypotenuse is equal to 10, how do you find the adjacent side, and how do you find the opposite side with respect to the angle that's given? And I hope that you are anticipating that we're going to be talking about using cosine and sine next. So again, up at the top here, this is the physics problem. You have a velocity vector as your diagonal. You want to find the component magnitudes, Vx and Vy. And so let me remind you about right triangles. And in math class, you learned that if you have a right triangle with an angle theta, that right triangle has different sides, which are described as the hypotenuse, the opposite side, and the adjacent side. And those are shown in the picture. Your math teachers always teach you about SOHCAHTOA. And SOHCAHTOA is a way to remember the trig relationships. SO stands for the sine function. The sine of that angle is equal to the ratio of the length of the opposite side divided by the length of the hypotenuse. The cosine of the angle is equal to the ratio of the adjacent side over the hypotenuse. And the tangent of the angle is equal to the ratio of the opposite side divided by the adjacent side. So these three trig functions allow you to establish the ratios between all sides of the right triangle. Okay, so this slide has a little bit of math on it, and what we're going to do here is write down, let's focus on the sine over here on the left, so the SO part. We would write that the sine of the angle theta is equal to, and instead of writing opposite over hypotenuse, we're going to write Vy divided by V. So here's where you have to look at your subscripts. Vy is going to be the opposite side here. V is equal to the hypotenuse. Usually what we do in physics is we just rearrange that. We multiply both sides by V. And so now you have a formula here for calculating the y component of the velocity. It's Vy is equal to V sine theta. That formula is a great one to write down because that's one that you're going to use over and over and over. How do you use it? You simply plug in the given velocity of 10 meters per second, and you multiply it by the sine of 37 degrees. Make sure your calculator is in degrees mode. If you're not sure, you can try it right now. You can try typing in the sine of 37, and you should get something close to 0.6. If you don't, you're probably in radians mode, and you're going to need to take a second to reset your calculator into degrees mode. So again, the sine of 37 should be 0.6. When you multiply 10 times 0.6, that gives you an answer of 6. And this answer is actually telling you how fast the object is moving in the y direction. This is your y component of the velocity. It's equal to 6 meters per second. The cosine function also can be used to find the x component. It's exactly the same thing, except now you take the cosine, which is equal to the adjacent over the hypotenuse. So that's Vx over V. Again, I would really encourage you to write down this second formula here, that Vx is equal to V times the cosine of theta. That's the one that we use all the time. And when you plug in here, you get 10 times the cosine of 37, which is 10 times 0.8, and that gives you 8 meters per second. At this point, it's good to just take a look and make sure that that makes sense. It looks like we're getting the bottom part of the triangle equal to 8, the vertical part equal to 6. That should be reasonable because this angle is small, and we would expect the base of the triangle to be larger than the height of it. So from a geometry point of view, that makes sense. We probably did it right. For the tangent, we're not going to use the tangent yet. We don't need it. So really the take-home here is to use the two components. And I'm going to stop at this point, and we'll start up a new video for part 2. Okay? So at this point, what we've learned how to do was we've learned that a vector is made up of x and y components. The components can be drawn by sketching in the sides of a rectangle, in which the original vector is the diagonal. And we've used sine and cosine to find the y and the x components, that is the magnitudes of those vectors. Okay, so we'll be right back.